Good morning, everyone. It is an absolute pleasure to welcome you all to the highly anticipated lecture series at AZeotropy 2025, where we have the opportunity to learn from some of the most influential minds in the industry. Today, we are honored to have with us Mr. S. Bharathan, Director Refineries at Hindustan Petroleum Corporation Limited, HPCL, a distinguished leader whose expertise has significantly shaped India's refining sector. We welcome you, sir. With decades of experience in the oil and gas industry, Mr. Bharathan has been at the forefront of process optimization, refinery expansion, and energy intensification. His leadership at HPCL has driven advancements and laid the steps that India has to take in the ever-evolving energy landscape. As the chemical engineering world transitions towards cleaner fuels and digital transformation, we couldn't have asked for a better expert to share insights on the future of refining and the roles that engineers will play in this journey. So, without further ado, please join me in welcoming Mr. S. Bharathan. Sir, we're truly honored to have you here with us today.
So can you see?
Distinguished professors of IIT Bombay and all my dear students and other industry colleagues, very good morning to all of you. It's indeed my pleasure to be part of this event today and one amongst you. I have given a couple of lectures in IIT Bombay earlier on different platforms, but this is the first time I'm seeing a full house, so very good and thanks to all of you for attending. First of all, I would like to give my credentials, why I am part of this and why I can speak in this technical seminar. 39 years back, I joined ACTech Chennai for BTech Chemical Engineering, and 34 years ago, I came out as a postgraduate in Chemical Engineering. And since then, I have been in this chemical engineering field throughout my career. When we joined, we used to always have a question when we joined the college. What you will do after finishing college? What will be the career like? What you will do? Whatever you are studying, where you will apply? So there will be a number of questions that is coming to your mind. And when we join the industry, again similar questions will come. Whatever we studied heat transfer, mass transfer, fluid mechanics, reaction engineering, so many things we would have studied, process control. So what do we do? Where do we apply these things? Should I carry my books to the place of work? So we have a lot of questions we used to have. But after I started working, we found whatever we did in the last 4 years, 5 years or 6 years, I will be frank enough, nothing is required to work in any industry. It's common sense which is required, but nevertheless, the problems which come day to day, there will be several problems to be addressed. The engineering what we study teaches us how to solve the problems and overcome obstacles, lay a growth path for future and so on and so forth. So that is what you'll have to keep in mind. But I myself realized after about 25 years in HPCL, I had an opportunity to head our research and development center. We have a HPCL Green R&D center in Bangalore, which is the youngest oil and gas research center in oil and gas industry. So when I had an opportunity to head the research center, then I found what I have been doing for the last 25 years was without understanding and appreciating the principles that has gone into the designing, the monitoring, the operations of the complex refining units what we have. We simply take crude and convert it into LPG, diesel, petrol, which comes to each one of our house for energy, for materials, and so many things which are there in the life, which have actually improved the standard of our living. So when I was in the heading the R&D, we came to know about the intricacies of each and every subject what we learned. The 4 years what we learn, if you really understand, go into the details, if your fundamentals are clear, then we are not only going to apply what somebody else has invented for us, but we ourselves will be the inventors. We will be in the forefront of any of the technologies, applications we get. Whatever we say, India is a country where we have been using imported technologies. We have been dependent on the developed countries for several decades. But that is no more true. We know the areas where we were deprived of the foreign technologies, we have excelled. The space science, atomic energy are some of the examples. But that's not the end. Now, even in the other areas and the new energy areas, we talk about energy transition, which will be the topic of my discussion today, the seminar today. We will see where the chemical engineering is applied and how what we have studied or what we are studying will help us India achieve the most coveted status of developed nation, what all of us want to be achieving in the coming future. So this is some of my credentials to start with. Now also something about HPCL. HPCL is one of the largest oil marketing company in India. We saw IIT Bombay started in 1958. One of the refineries in Bombay was started in 1954. We have another refinery in Visakhapatnam which is started in 1957. These are the refineries which have started as the Mumbai refinery was started by Standard Oil, US. The Vizag refinery was started by Caltex, which is also an US-based company. But in 1974, Government of India took over these assets and amalgamated into HPCLs. And for the last 50 plus year, last year we celebrated our Golden Jubilee celebrations, 50 plus year, we are existing as HPCL. We are also building a new refinery in the state of Rajasthan, which is coming up in a place called Pachpadra. We have a joint venture refinery in Punjab, which is called Hindustan Mittal Energy Limited. We also have another joint venture in Mangalore, which is called Mangalore Refineries and Petrochemicals Limited. These are our refining assets. We have, for logistics, we have storage and terminals all over the 26 states of India. Also, we have almost 23,000 retail outlets where most of you would have been going one part of the time of other to get some part of energy, some source of energy which you would have been seeing. So this is about HPCL. I'll straight come to the topic, role of chemical engineering energy transition. This is not a lecture, or this is not a lecture assembled by a college professor. So this is what from an industry perspective I'll be talking. Since I have not been making notes or not repeating these lectures, I will have to refer to my slides frequently and I'll read out. Pardon me for that. The topic what is mentioned, I think it was written, applications of chemical engineering energy transition. Never mind, both of them more or less will be same. I will talk about what is energy transition. Many of you would have been reading such topics which are actually the talk of the town for the last 5-6 years, and then tell what from an industry perspective we are doing to reach that, handle the energy transition, how chemical engineering is helping us in achieving this energy transition, and end by some of the works what we are doing from our research center. Next slide, please. See, global climate change, we all of us know the climate is warming up. We would have read several times that the temperature rise has to be contained within 1.5 degrees if we will have to sustain our standard of living or sustain the environmental climate conditions. And also we know that this is not possible and it is going up. In the coming years, we know the earth is going to be heated up, and then we are going to see all the climate changes. The atmospheric gases, which is the carbon dioxide, methane and some nitrous oxides, are actually preventing the radiation that is coming from the sun to escape back. When the amount of energy that is coming from the sun, it radiates and goes out back, then the temperature will be constant in the earth. But the gases that we have are actually trapping that heat, because of which the earth is getting hotter. Next slide, please. Now what will happen? This is known. We have been reading, everybody says. But actually what is going to happen because of that? If we don't contain within 1.5 degree ambitions, the temperature rises. If it is not going to be there, then your GDP is going to get wiped off by almost 13%. If it goes to 2 degrees, it will be wiped off by 13%. And you will be seeing 4 months of drought and several weeks of floods. That is what we are going to see. If we are, the current path which is actually telling we may reach 4 degrees in the next 3-4 decades, which is actually going to wipe off the GDP of the world by 30%. And we will be seeing 10 months of drought, and the balance 2 months are actually going to be floods. This is what we are going to see, and some parts of the world we are already seeing. Next slide, please. Now, apart from the climate change and the gases, what I told, which are going to trap the heat, there are several planetary boundaries which we are supposed to honor. There are 12 such boundaries listed here. Climate change, one of them is climate change. Apart from climate change, we should also have biosphere integrity, stratosphere ozone depletion, atmospheric ozone, aerosol loading, ocean acidification, the land and system usage change, freshwater use, and so on and so forth. 2009, we had just violated about 3 of them. In 2015, we had violated more than 4. And in the 2023, next, we have now violated more than close to 6 boundaries out of 9 we have crossed. The predominant being the climate change and CO2, which part of that is the CO2 concentration. Now, 1 or 2 I will just explain what is that. Biosphere integrity is the the old species which are disappearing. Many of the planetary and animal species, we know they are all nearing extinction because of the ecological changes that is taking place. Water, we know, even cities like Mumbai or Delhi, we know during summer we have the challenges of availability of water, which is affecting the entire society, and many others are there. We will not go into all these aspects, but we will see how this climate change is affecting us. If the planet's boundaries are the safe limits for human pressure on the 9 critical processes, which is required to be maintained if you will have to live as we are living today or as we lived a century back. Next, please. Now come to what are the different terminologies or terms we have been seeing. The first is energy dilemma. Energy dilemma is what I will go to transit. Should I go for renewable energy? Should I go for nuclear energy? Should we curtail our energy usage? Should we be increasing any other forms or continue with fossil energy? Invent means of reducing the pollution. So you have a lot of solutions we think about. But one thing what is clear is we have still not found out what is exactly to be done. There are many areas which has progressed, but that they are all not going to take us to the goals what we have. So that is what is called by energy dilemma. We have a dilemma today on what is to be done. But there is, if somebody is going to solve this dilemma for this world, for the humanity, there is only one group of people who will be capable of doing. So I will tell that towards the end. Even if I miss, please ask me during the question session. So who are the people who are capable of solving this energy dilemma? Now comes the next term is the energy trilemma, which is energy cannot be, I cannot completely switch over only to a net zero energy, but it should be also be affordable. It should be affordable to the weakest parts of the society. It should be secured. I should get throughout the year. If I'm going to import a particular energy and then some geopolitical situation happens, then you may not get throughout the year. So the next aspect is the security, and it has to be sustainable. Whatever we do, it should be sustainable. So that was the term which we coined about 5 years back, that energy trilemma is important and not just energy transition. But last year or about 2 years back, the another term has come, which is energy quadrilemma. Energy quadrilemma is these 3 aspects plus whether it has been accepted by the society. Now you can always say this is what we have introduced, now we will have to follow. But if the society doesn't accept it, then that forms of energy will not come. One example is the atomic energy. If atomic energy is there, we claim it's the most safest or cleanest energy form. And the people who are around the area who feel their livelihood is being threatened, then that means the energy is not accepted. So we have a duty. We will have to explain that the exact impact of what we are doing or the benefits of whatever solutions we are doing, then it will be accepted. So it will be accepted in the society. So the quadrilemma takes care of the three dimensions of the energy transition, including the fourth dimension is social acceptance. So these are only some of the terms which many of us keep talking about, but in the coming future, more such dimensions also may get added. Next, please. No, it is possible or not possible. That is the question we will address. Actually, it appears it is possible, though the rate is very, very low. In our own country, if somebody 10, 15 years back had thought about the solar energy penetration, they would not have thought in 2025 this much development or this much achievement we could have done. Today, more than 27% of the peak energy is being supplied by solar and wind, which was not thought of about 12 years back. That means this is possible. And 8 countries in the world have actually declared they are already net zero. The countries are listed below: Bhutan, Gabon, Guyana, Madagascar, Suriname, some of them. If somebody can think about how these countries, what is the similarity in these countries, how these countries have already declared they have net zero, it's quite easy to guess. If somebody can think, you will get the answer very easily. If you are not able to get, again, please ask me at the end during the question period. Electrical vehicle also, we have been hearing maybe from 2000, early 2000 onwards, electrical vehicles are there. In the first decade, it grew very slowly. Second decade, we thought it will grow very fast, but it didn't happen. But in the last decade, the current decade, it's really penetrating a lot. So shortly, we will be seeing, at least in some of the countries like Norway, new fossil fuel vehicle growth is very, very low. More than 90% of the new vehicles that are sold are only electrical. That means in some part of the world, it is transition is already taking place. It will gradually shift to our countries also. So clean energy investment has reached a record $1.8 trillion, which is 60% of the total energy investment that are taking place. Now less and less money is going into oil exploration and more money is going into the alternate forms of energy. But this is having both a good aspect, that in future we know that less of fossil fuel will be there and more of clean energy will be there. But the con is, if the energy demand is so high and we are not able to meet with renewable, then many of us will be facing shortage of energy. So both, there is a plus and minus for this. Some of the points I've listed are how the infrastructure is going on these renewable things and how the cost of renewable energy has come down in the recent past. Yeah. Now, whatever has happened so far, if you will have to maintain the temperature rise at only 1.5 degrees, which was our target, to maintain the same climatic conditions in the world, we have reached only 2.6% of what is supposed to be done. We have just reduced 2.6% of CO2 in this last 5 or 6 years. Now whereas our requirement is to reduce by 43%. By 2030, if you want to restrict the temperature rise, the requirement is reduced by 43%, but we have reached only minus 2.6%. So this is the challenge and reality. Actually, at this rate, definitely the temperature rise is going to be more than 3 degrees in the coming 3-4 decades. Next. Now, what are the key strategies which as an industry we do, what we have identified? This may not be the only solution, but these are the things which you are doing, and on some of them there is a very good development and penetration, but there are some areas where we are not able to do much. The first one is renewable feedstocks and renewable energy, which we have already seen in the previous slides. So India is today blending 20% ethanol in our petrol, whatever we are using. That means 20% of the fuel what we are using is already renewable, or it is coming from biogenic source. Similarly, biodiesel we do about 3-4%, biogas about less than 1%. But in the coming days, this will increase. Even the aviation fuel will be introducing sustainable aviation fuel, which comes from biosources. So here there are some good development that have taken place, which is being reducing our carbon footprint. The next thing what all of us have planned is to do green hydrogen. Now, hydrogen is the most cleanest molecule you will ever see in the world, because it just gives, when it burns, it gives only H2O. So there is a no-brainer, and it's known for centuries. Then why this has not grown into a most, or as the alternate fuel? It's not easy to make hydrogen so simple. I mean, you can say in an easy way you will do, but it is not that easy. That's why it has not grown as otherwise would have done. Because even in 1960s, the hydrogen-powered vehicles were already invented and ran in some of the countries, but it did not grow because of the cost factor. Now again, there is a traction that has come back because the renewable energy costs or prices are coming down. We feel the power that goes for making hydrogen by water splitting reaction will be the next form of alternate energy which can come. We at HPCL Vizag Refinery, we have put India's first electrolyzer in any Indian refinery. It's about 370 tons per annum, which is up and running for last 1 year. And we want to scale up to such an extent that the entire hydrogen that is required in any Indian refinery. Typically in a refinery, we require 1 to 3 weight% of the total crude processed as hydrogen to do various reactions. If that can be converted into green hydrogen, so most of the emissions from a refinery can be brought down. That's only for captive use. But hydrogen can also be used as a transport fuel. You can use it directly in an IC engine, or you can convert into a power through a fuel cell and use it for mobility. So hydrogen is having such applications also. Energy efficiency is a low-hanging fruit. Whatever we do, you do it in a better way, energy efficient way, your carbon footprint is going to be low. So this is being done by all the industries, and this is one of the leading steps that has been taken for reducing the CO2 footprint, and this gives return also. So there are several things where you'll have to spend money. Here actually you get good returns. Carbon capture as utilization is again another term which is usually talked about, but definitely it has not grown to the way it is supposed to have been done because again of the cost factor, the technology breakthroughs have not come. Carbon you may capture, but it takes a lot of money and efforts to capture the carbon. And after capturing, what you will do with that? That is another question. You cannot just inject into the earth and say, I have sequestered. After some time, where is the space for putting the balanced CO2? It can be one form of removing carbon, but that is not the only solution. So you must be able to convert the CO2 into any useful products. Now CO2 is the most stable compound you will ever see. CO2 is very, very stable. You just cannot break that CO2 into C or O2. And if you can do that, if you can partially reduce, the moment you get a carbon monoxide, then you can do a number of chemicals you can do. You can convert into various other forms. So these are the areas where the new generation is expected to work and deliver some results for us. Second is the next fifth one is the circular economy. Whatever waste we do, we now reduce, we recycle and reuse. That is the mantra for the circular economy. So we try to bring in pyrolysis oil, which is again converting plastic back into fuel. We do mechanical recycling of plastics. The biogenic generation, which is the rice straw, paddy straw, whatever is waste after the food has been removed, can be used for generating ethanol or any other chemicals. So that is the circular economy. And finally, fuel switching into the power, low carbon fuel. Low carbon fuel is natural gas. If you are using a petrol or diesel, the CO2 emissions, if it is something like a factor of 10, when I use a natural gas, the factor comes down to 6. So that switch itself reduces 30% of CO2 emission. These are the 6 known strategies of energy transition today, and they have all been implemented in the various degrees of penetration. Yeah, next please. Just a small diversion, many of you will be knowing, you would have read some books or during the initial classes, people would have covered this. Some of the fascinating facts of chemical engineering are today if all of us are able to eat food, in spite of India's population multiplied by several folds from the day we got independence till today. The population has grown by almost 4 times. But for all 4 times, people, we are able to give them food. So how we are able to give it? Simply because synthetic fertilizers have been used. The fertilizer industry has actually led the green revolution, and all of us are able to get food without any problem just because of fertilizers. And fertilizers have come because of Haber-Bosch process, which is the conversion of nitrogen and hydrogen into ammonia, and then we convert into urea and make all sorts of fertilizers which is coming from that. If the crop or whatever agricultural produce it is able to do, It's only because of the chemical engineering process, which is the Haber process. Now the next is the plastic revolution. In a lab, normally we do several research when we do number of materials people will keep on identifying, developing. So one polyethylene was one such material, several century back it was identified. But today polyethylene is one of the most sort of plastic material without which the standard of living what you have reached would not have come. It is there in each and every part of the life today, which has made the accessibility and affordability for many of the material within our reach, which is again come from chemical engineers like us. The next most important is the life-saving drugs. So these life-saving drugs, today the life expectancy has gone much more than 70 years from low 50s several decades before because of the advancements made in the pharmaceutical industry. And all these pharmaceutical industries, chemical engineers have developed processes, material, solutions for overcoming many of the pandemics that were existing in our world. One more main important, like the food, is water purification. Water is another key resource for us. And as the population grew, water became scarce. But because of water purification technologies, we are able to give water to the entire society even now. There are problems at pockets, but as the more and more breakthrough comes, in a more affordable way, we will be able to give water for all our requirements. One more, just put another invention is about the astronauts where they went. We have heard about use of pencil in the spacecrafts. You have even ball pens which will flow in spacecrafts, so on and so forth. All have come through some innovative ideas of chemical engineers like us. Next, please. Some of the facts you would have known. Now, some of the, just go touching about the history of chemical engineering. Ever since the your Bronze Age or the Metal Age started, chemical engineering have started from then on. We have been purifying, we have been converting into various forms. Then for perfume extraction, chemical engineering principles were used. These are all 3,000, 4,000 years back. Definitely there were no colleges or chemical engineering curriculum at that time. And another most notable item which people were always talking about 2,000 years back, that many people claimed they will convert bronze into gold, which is the alchemy. But they were all attempts made, sincere attempts made to do some changes to the molecules. Next, please. Now, organized chemical engineering field, how did it come? Organized chemical engineering, the industry what we have, how did it come? It started with, in UK, most of the developments now was taking place in the Northern Europe or Western Europe countries. So when the glass industry was going, the need for soda ash was there. So from batch process, they went into a 24/7/365 industry. So the first such industry was soda ash industry. Then it changed into our textile industry, where dyes were started making. The chemical engineers started producing dyes which were required for our textile industry. The number of other similar processes gained traction towards the beginning of 20th century. And the first recorded academic progress, the series of lectures which was made at Manchester Institute of Technology were all documented, and the first curriculum started in sometime in 1887. In 1888, first chemical engineering curriculum at MIT US was started. So this is a brief history, and subsequently with the advent of the horseless carriage, which are the transport vehicles, then the fuels came into being, which we are all using till today. Next, please. Similar information, I have just put it in a different bucket. In the first 1930 to 1960, when the World War came, there was a requirement of a lot of new materials. Chemical engineers stepped into each and every requirement and solved the requirements or solve the problems of the World War II. Today we have high octane gasoline. You get the gasoline what we buy from the petrol pumps are having an octane number of 91. When the World War II broke out, there was a requirement of high octane gasoline for running planes. And the country which could make huge quantities of high octane gasoline actually won the war. So that is the importance of chemical engineering, not only in the lab scale development, but in the industrial scale production also. Petrochemical industry, we have already seen. Advancement in unit operations has actually helped us in improving the efficiency of production, and the cost of production as we are able to bring down. The 1960 to 2000, the advent of computers came, so the process control came into picture, and now the efficiency even more it went very high, and the manual intervention has reduced. Today, chemical industry is a place where less number of personnel you will be seeing in the process plants because of advent of the computers and process control. But at the same time, environmental regulations also had come. See, when development take place, there is a negative thing that is also happening because we, some way or other, there is some emission into the our environment. So we will have to grow in a responsible way. So the rules and regulations started coming when this all got accelerated. Biochemical engineering was another area which started prominence about 4 decades back, and now it is still in one of the most sought out or most having a promising area where more developments will take place. The last 20 years, we will say we were, as we saw, renewable energy integration is taking place. Nanotechnology and material science, we are not satisfied only with the new petchem or petrochemicals what we saw, or some of the new metals what we saw. We require now more and more new materials. Even now we are looking at. Suppose I told about hydrogen. Now if you want to make hydrogen at a lower cost, at the same time don't be import dependent, then you will have to bring new materials also into picture. Digitalization and industry 4.0 is again which is going to take us to the next levels. Yeah. Now we will see some more areas where the chemical engineering principles are required to be applied, which will help us in the energy transition. Energy efficiency we already saw. But the processes that require less energy for any heating, cooling. Any chemical process will involve heating, making a reaction or a physical separation, and then you'll have to cool back. So it is an energy intensive industry because of that. If we can integrate the energy recovery system, if we can reduce the energy, then that will be of help, which we as a chemical engineers, we will have to find out a lot of new innovative methods to achieve the same. Reducing the equipment size. We are looking at miniaturization, process intensification, the land footprint, the carbon footprint. Each and every item what we are telling has to be at a smaller size. So that is reduction in equipment size is another important area where we are doing, which is called process intensification. Again, we handle flammable liquid. It's very dangerous materials we handle. So whatever we do has to be in a safety also. So industrial safety is another area where growth is required, or newer concepts will keep evolving. Lower environmental impact, I have told, increased throughput and productivity with a given amount of raw material is also one more area, and process innovation. I would not have told something. Tomorrow's new invention are today not known. That is called technological breakthrough. You may not be able to tell what is that solution that is coming today. If some of you can bring out that becomes the breakthrough technology, like electricity. When it was invented, the electric bulb was invented. The previous day, nobody knew that such a thing existed. So when such thing comes, it is really a breakthrough. This is what is required rather than an incremental improvements what some of us are doing today. Next, please. Some more key trends shaping the future of chemical engineering are applied AI and generative AI. As we use this in several business applications. In industry also, if you use this, you will get that incremental improvements coming up. More better predictions can be done and better optimization will be there. Robotic process automation follows that. Some areas where we were not able to reach earlier, now we are able to reach there, and a repetitive task can be easily done by a robotic process automation. Now molecular modeling and simulation. I was mentioning you will have to go to that molecular level of valorization. So if you have to do, I cannot do thousands of experiments and come to a solution. So you must be able to do that same thing through molecular modeling and simulation. And in a refinery like ours, we process raw material from almost 20 to 30 different sources. Crude can come from across the globe, anywhere it can come, and each type of crude will have different set of properties. Now if you will have to seamlessly process that, you should be able to predict what will happen when such a particular crude enters the process plant. That is where the process simulation helps us in real-time optimization. Quantum computing helps us in achieving the speed, what we could not do earlier. Now by applying the quantum computing principles, we will be able to do. and industrial machine learning also, right? So now what are the sustainable green technology? We talked about green hydrogen, green power, recycling, carbon capture. Some of the items which are highlighted red are, I will touch upon now. E-fuels is synthetic fuel, which is made by absorbing CO2, using the renewable hydrogen and making a fuel out of it. So e-fuel is one which is thought or which we feel in the coming years, if we can make it in an affordable way, then in the existing infrastructure, without changing any of the supply chain management with the existing retail outlet, with the existing petrol pumps, you will be able to achieve energy transition. So e-fuels is one which is touted to be a future, but today it is definitely not economical. One more field where as a chemical engineers we can contribute are in the catalysis. Several years back, India started the journey for removing pollutants from the fuel. We had started with the Bharat stage 2, where 2000 plus ppm of sulfur in the diesel was reduced. We used to have almost 10,000 plus ppm of sulfur, which was reduced to 2000. 2000 we brought to 500, 500 to 50, and today we are at 8 ppm sulfur in the diesel. That means I have removed the entire contaminants that are there in the fuel. Drastically, sulfur dioxide emission have been reduced because of this advancement. Now, how you would have done? It is easier to remove when the sulfur is high at, say, some 10,000 ppm to 2000 ppm. And you go from 2000 to 500, it becomes severe. 500 onwards, when you want to remove the refractive sulfur species, it's very, very difficult. It's energy intensive. It requires a lot of volumes of catalyst to do it. But we are all able to do without any problem in India. From 2000 onwards, the entire country is producing less than 10 ppm diesel and MS. Now, how was this made possible? In the same reactor, just by advances made in the catalysis, we are able to do the same thing. Catalyst, we were looking into the pores, we are putting the active sites inside the pores, we are putting a structured stacking of the active sites is being done, and whatever I am telling are all taking place on atomic level. So that is the growth in which catalysis has helped us today, and we hope in the coming days further it will keep on be growing. At every time we think catalysis has reached the maturity level, there is a new invention which takes place which further reduces either the energy or size of the reactor that is to be done. So catalysis is in one area, energy storage is in another area. The renewable energy has a problem of variation. Wind is not available throughout the day, so sun is not available throughout the day. It is seasonal. In rainy season, you may not get these two. So what is to be done? That is where the energy storage is required. If you want to supply only renewable energy throughout the year, then energy storage is very, very critical. Today, though the renewable energy has grown, in periods like summer where India's last year demand crossed 220 gigawatt, so where is it suddenly going to come up? And in the night when our sun goes down, the entire 220 megawatt has to come from fossil fuel. So that is the problem which is there today. So in spite of advancements made in renewable energy, when the peak energy demand is there, it is fossil fuel which is stepping in to satisfy our needs. So if you will have to overcome that obstacle, energy storage is required. Now energy storage is again a costlier solution for us. We know the battery prices are coming down, but more novel concepts are required. Somebody talked about pumped storage, somebody talks about compressed air and then taking the energy later, so on and so forth. One more is crude to chemicals. We saw a lot of advanced materials has come like polyethylene, polypropylene. They all require more than 10 to 15 processes when you make. What if I can just take the raw material, which is crude, and in a single step, convert into ethylene and propylene. So that is crude to chemical, single step process, on which very good work has been done. And from HPCL side also, we are putting up a demo plant in one of our refinery to achieve this single step conversion into chemicals. Next, please. In future, we feel, as I already mentioned about material and nanotechnology, biocompatible polymers, these are the areas where more research, development, deployment are required. Energy storage we have seen, so we'll go to the next. Now, what is the traditional chemical engineer what was doing, and what a future chemical engineer will be doing? Traditional engineer, the focus area was process optimization only. Future ready will be, along with process optimization, we'll be focusing on sustainability, green energy and circular economy also. Energy sources are only fossil, now we have multiple sources. Technology usage will be conventional process engineering tools, what we have been learning, but future that alone is not sufficient. We should have more of AI, machine learning and digital twins that are coming up. In product design, we were focusing only on mass production. Now even the green chemistry and eco-friendly products are also to be seen. The innovation approach, collaboration. This is just a listing of what so far has been happening and what a future-ready chemical engineering is required. Next, please. I can also add to this by telling that, see, many of you are attentive in any class. The front benches are normally very attentive and they'll be taking notes. But as you go back, the backbenchers will be there who will do what they feel like. And maybe they are also right. In their own world, they may be thinking something, maybe new ideas are coming. But the traditional versus conventional, what we see more and more backbenchers are now growing. That is another kind of challenges before probably the college should be handling this. Okay. Now the similar solutions what I had wrote for chemical engineers, product innovation, process innovation, and the ecosystem. Whatever we do, I have been keep on repeating, it has to be done without impacting the environment. So these are the ones which is required. Innovations are required in products. Innovations are required in process. That means new and new molecules, new and new combinations we are looking at. The way we do, we are looking at new processes. As I told, single step conversion to crude to chemicals. And whatever we do should be sustainable. So these three show what is the scope for innovation for chemical engineers. Next, please. Now, this is what I had just covered about energy transition. All of us know climate change is very important. We'll have to focus our areas to grow on this sustainability. Then I touched about few things on how chemical engineers are helping in achieving this energy transition. Before I end, I will cover something what HPCL is doing for this innovation. So as I told, we have the youngest oil and gas research center in Bengaluru. Within this 10 years, our patent portfolio has crossed 650 and more than 10% of this, 10 to 20% of these patents have been commercialized already. So it's not only for doing sake, but it's all done with a purpose. There are several areas. The current thrust areas for us is indigenization of catalyst chemicals, process intensification, biofuels, petrochemicals, and alternate forms of energy. These are the current research areas. There are more than 21 labs in that within that campus. The basic principle what we use are we apply the principles of green chemistry in each and every project or each and every activity that is being done. It will be starting from waste prevention, use of safer materials, safer chemistry, and real-time pollution prevention. So there are 12 principles of green chemistry. You can there are books written on that. You can go through that and see how each one is applicable and how each one of them is very critical for future growth. So this is being applied in all our research activities. By these applications and by the facilities what have been created, some of them have been already brought to the commercial scale. So few of them are listed here. One is the HP code, which is crude to olefins and aromatics technology. I have already touched upon this. The second one is blue hydrogen. Now CO2, I told you, we'll have to cost-effective way we'll have to remove. So that attempt towards doing this, the HP BH2, where 21-meter column, you would have learned about distillation columns, where a 20-meter, 30-meter tall columns will be used, is being replaced by a 1-meter diameter rotating packed bed. That means the mass transfer which was taking place in a long column of 20 meters now can be compressed to the same mass transfer will take place in a 1-meter rotating packed bed. The mass transfer forces now come from the rotating motion of the bed what has been made. So one such attempt is we are setting up a demo plan. Already there is a pilot running in our R&D center successfully. The next verse is another indigenous technology which is trijet. Trijet is triglycerides to jet fuel, which is nothing but conversion of vegetable oil or a used cooking oil into sustainable aviation fuel. Right. There is one demo plan coming up in one of our refinery also. HP ASAP is acid assisted single step conversion for the production of ethanol. So there is a pilot running. We are planning to put up a demo based on this. This converts the waste agricultural product, which is a rice straw or a wheat straw or a bagasse coming from sugarcane, can be converted into a fuel. Similar thing is RAMP, which is rapid acidification for methane production. the same biogenic feedstock can be used for converting biogas also. Actually, biogas is more efficient than the ethanol route. More than 14% of the material right now we are able to convert into gas. HCNG is another form of alternate fuel where hydrogen is mixed with compressed natural gas. There are various ways of doing. I can simply produce hydrogen separately, mix with compressed natural gas. But the effort what we are doing is you take the same natural gas, pass through a reactor where a partial pyrolysis takes place. The partial pyrolysis will convert part of the natural gas into hydrogen by rejecting carbon nanotube. So carbon nanotube brings value. If we can add value to that, this entire alternate fuel becomes a value-added solution for us, and it will be sustainable. There is a pilot running for that, and demo plants are being set up. Yeah. Several other green technologies I can keep on be talking about in other forms. I have been covered most of them, but some we can talk about the new electrolyzers. Solid oxide electrolyzer is the most energy efficient electrolyzer which will take the power consumption close to the thermodynamic limit. So that is being made, and there are several other process intensification and cost reduction measures that are being done. Bio-based polycarbonate is one. We talked about new materials coming and material innovation is to be there. So these are some of the examples of innovations going for a new material, which is polycarbonate and polylactic acid. These are true 100% degradable and renewable products. Yeah. We'll have some more time for questions, so I'll rush through and close this. Circular economy is one. Spent lube oil can be reused. Yeah. There are several chemicals which can go for energy efficiency improvement. You may invent a synthesis, a new molecule, or you can do a synthesis, a new formulation. By formulating different things, you will be able to achieve the energy efficiencies, what you have been doing, overcome a lot of the process problems, what all of us see in the industry. So these are some of the examples which are all commercially used in our refineries. So to summarize, the dynamic nature of chemical engineering ensures a constant stream of innovation. I told in the beginning, energy dilemma. Who in the world will be able to solve the dilemma we have for how energy transition should take place, and how will we make solutions for that? If it is a one group of people who can do, it's chemical engineers will be able to do. So believe me, the solutions are there in chemical engineering if somebody is talking about energy transition. Other things we have seen again, so we will not repeat, like waste minimization, reducing emissions, continuous advancements in process automation, optimization. In each and every aspect of energy sector, chemical engineering is the backbone. So to repeat what I told, to achieve energy transition, to overcome the energy dilemma, again to achieve the energy quadrilemma which I told, chemical engineering is used in all spheres of these areas. Hope some of you will be part of us in the coming days in achieving this objective. Many of you will be working in these areas across the globe in some form or other, who will be working towards achieving this great. So all the best to all of you and best wishes from my side. Thank you. Next slide, anything? Right. So we have some time. I mean, I think I have till 12. Something. Who are the organizers? They are all outside busy. No problem. I can take few questions. You can ask me anything, whatever is possible, I will reply. Yeah.
What do you see the potential of hydrogen carrier, like in the form of some materials?
So we talked about energy storage. I told because of the variations in renewable energy, unless you have a storage solution, you will not be able to either use it throughout the day, or you will not be able to move that from a place where it is available and take it to a place where it is required. One example is hydrogen. So now hydrogen cannot be transported to large distances in an economic way. There are different solutions that are required. Australia has huge portions of land where I can make solar power. I can convert into hydrogen. But who is going to use hydrogen in Australia? It has to come to Asia. But how it will come? So that is the question mark. So his question was towards what is the carrier for hydrogen. Now carrier for hydrogen, there are many. Again, chemical engineering has answers for all. Ammonia is a carrier. Liquid organic hydrocarbon carriers are there. So there are many solutions are there. But like any other energy solution, energy storage solution, this is still not economical. So the duty of us is to see how do we make it economical. Then somebody came out with another idea also. You are trying to make a chemical molecule and then trying to move. What if I make an electron and move the electron first, use that electron to convert the chemical molecule? So here probably electrical engineering also we should collaborate. If I can lay a cable from Australia to India, power can come here in an economic way, then we can convert that at the point of requirement. I think these are the exciting things which have to come in the future. Yeah. I mean, you can ask any questions, not only about the today's presentation or generally about the industry, about HPCL or any other thing which you would like to get a perspective from our industry. Yeah. This is not a class question, so students should be happy to ask. Yeah. Yes.
So, do you perceive that the requirement of fuel will go down, so the refineries is there and endeavor to focus more on other products, being cut off to that goes into fuel?
Yeah, I mean that is one of I showed 6 strategies for energy transition. Some part of the world already the fossil fuel has actually started reducing. Some part it has formed a plateau, and some part of the world it is growing. We are in a part where it is growing. If I will have to stop suddenly and then jump into the alternate, then there is going to be an affordability and sustainability issue. So it will happen gradually. Definitely as a company, we have our own objectives for reducing scope 1, scope 2 emission and scope 3 emission also. Scope 3 emission is what your question is towards. So we are also focusing on diversification all, but at the same time, the core requirement for the country also has to be met. So we have a dual duty of maintaining the core without which we cannot survive. At the same time, for long-term sustainability, go into the alternate areas. So both are there. But as I told, there is a dilemma on how to do it. That is where we are looking at solution from large groups like this. Right.
Regarding HPCL, whether they are focusing on coal gasification?
Yeah, coal gasification is another promising area because India is abundant of coal. Why we should buy crude and convert? Why can't we use coal? But from HPCL point of view, we have prioritized our areas. So right now we are not looking at coal gasification. There are somebody else we know they are doing. We are looking at the other areas like hydrogen, the renewable source conversion, biofuels. So we have prioritized accordingly. Yeah. Wastewater, I put in the history of chemical engineering, water treatment is one area which has actually helped people to get water. Otherwise, for this much of population, you would not have got. Initially, it was started by just taking some potable from a river water, purifying to make it potable. Then it went to a deep well, going into a bore well, and then purification. Now, all the sources we are reaching the maximum that is possible. Then comes the question of recycle, which is the wastewater treatment. Most of the, we have technologies today to 100% recycle any water that is coming. Any industrial effluent can be converted into potable water. Some easier effluents are easier to do, but everything comes with a cost. So some of the easier, milder pollutants we easily do, but when it goes to very severe, then it is quite difficult to do. Good progress has been made in wastewater treatment. Our own refineries are today zero discharge refinery, meaning 100% I recycle the entire water after treatment. There are areas where it is still difficult, like we see pollution that take place in rivers. That means there are difficult pollutants are being left. So the future of wastewater treatment will be in that difficult area, whereas in majority of other area already it has reached quite good level of technology maturing. But still we are looking at new areas for this difficult pollutants to be treated. But this is one good area which is going to be for a long time people will be working on these areas. Right. Yeah.
Question is so there will be some release of CO, biogenic CO2. So there is any like idea for utilize that biogenic CO2?
Yeah, right. His question is when you are producing ethanol or in fact even CBG, it comes along with CO2. Though the CO2 is taken as the renewable one, that is not the net release. If you can remove, we will move towards a net negative technology. We should not reach only net zero. Unless you go to net negative, you will not be able to reduce the CO2 concentration in the atmosphere. So what we are trying to do is, this CO2 can be actually captured easily, I already told. But as I also mentioned, utilization of CO2 is important. I absorb and then do what? If I can do a better way of converting into a chemical or a fuel back, then this will grow. So these are all at very preliminary lab levels. We are actively working on converting into some useful chemicals. Yeah.
Regarding there are some analysts saying that by 2050, the coal production will come down by 7%, and oil production will come down by 4%, and gas production by 3%. So in this scenario, what is the diversification, like oil and gas companies taking place or doing?
More or less a similar answer what I gave. We'll have to keep the development, because we are in a part of the world where it is not going to happen in 2050. It may happen in 2070 or 2080, it will happen. Our own Prime Minister announced that by 2070 we should reach that stage. But till that time, this will be growing only. Even today, as of 2025, oil is growing at about 3 to 4%. Gas is growing at about more than 10% because it's more cleaner. When these two are going, plateauing of peak oil is anybody's guess. We have been hearing that for the last 20 years, but it has not peaked. Probably it will happen when we are all there. Let us see. But next 3-4 decades, I don't see that. So we are in the core, at the same time looking at quick opportunities to grab the new energy areas. Right. No other questions, or one last I can take. Whoever is there, otherwise we can end. Yeah. Yeah. In current situation, where are they going to be used? In industry, I told we use hydrogen for purification, removing all contaminants, and for secondary process like hydrocracking. Hydrocracking is in the presence of hydrogen. If you crack a heavy hydrocarbon, then you will get more useful products like petrol and diesel. So that is the use in any industry. Alternate form is I can use it for mobility. Mobility is IC, I can use hydrogen in the IC engine. We can use hydrogen for power generation, for onboard power generators in a car or truck. Hydrogen can be used in other industries where it is very difficult to achieve net zero. So hydrogen has applications everywhere. As we saw, hydrogen is the most cleanest molecule which can, when it burns, it doesn't give out any other contaminants. So that has a promising, and the challenges are many which we saw. Few of them we saw, but many more are there. Hope you will be part of overcoming those challenges. Right. Thank you all for patient listening. Thank you very much.
Hello. Yeah. Thank you so much, sir, for your time and valuable insights. I would like to invite Professor Roches to present a token of appreciation to Bharathan, sir.